Good evening, Professor Amamura. You did require all 200 services listed in our first assignment.
Yes, that is the case. There's probably easier ways than others to collect that information, but it shouldn't be too painful of a task. I've had this exercise since this course has been available, so Amazon, excuse me, Amazon and Google probably have grown their product catalog since over time for obvious reasons, but yeah.
But just AWS, the 200 services from AWS, not anything from Google.
So yeah, great question. So you actually should see in Canvas both 1A and 1B, which are the same exercise, but for AWS and for GCP respectively.
Okay.
Okay. Happy Thursday to everybody. Welcome back. We are in the second lecture of the course, and given that folks are still filtering in, we'll give everyone who will join us today some time to join, and we'll get started at 5 after the hour. I'm happy to answer any questions in the interim before we actually get started, but feel free to use the Zoom chat or ask away uh, if you have audio. We'll get started at 6:05 p.m. Was there a question you had, Dylan?
Yeah, so regarding the lab and stuff like that, like I'm currently reading it and stuff, right? So like for example, like the assignment 1A and stuff, where it's asking us to identify slash describe and classify all current virtualized resources provided by AWS. Are we supposed to search up AWS as a provider and then just classify what they give or what they have in service on a like a document, or is there something specific that we have to do? Because I'm still kind of confused, and I'd like to get this lab out or this assignment out as quickly as possible.
Right. So both Amazon and Google Cloud Platform have their websites in which you can access to view their product offering. Um, Within each of their product offerings, they have different service offerings that are offered in their cloud services platform. So the idea is that if it's a spreadsheet, if it's a Word document, you want to be able to collect all of the different metadata around the services that are offered for both providers in a way in which you wouldn't have to go back online if I asked you what is Amazon Cloud Formation or what is Amazon S3, right? That is the exercise.
Okay, got it. Thank you.
Okay, we are 5 after the hour here, and that should mean that we should get started. So, thank you all for joining today. Hopefully everyone's had an opportunity to digest the first class we had. A recording has been made available in Canvas at this point, as will happen after every course that we have live in Zoom here. Can everyone hear and see me okay? I want to make sure that I'm transmitting clearly in any form or fashion. Yes, I get some thumbs up here. Acknowledgement, great. Okay, so there seems to be some questions related to Lab 1A or Assignment 1A and 1B. I'm going to quickly walk folks through that before we actually get started to clear the air on anything related to the lab. So let me find my screen share here. And we're going to go into Canvas. All right, so Lab 1A here, it refers to Amazon Web Services. Lab 1B refers to Google Cloud Platform. Both are 10 points each, but if you were to go to Amazon Web Services website, look under their product offerings, you're going to see a list of different offerings that they have. This is their product list, and you have a variety of different product offerings with their headlines for each. The idea is we want to have, you should be able to pull this information and classify it in a document for your own reference. You can create links to it as well and expand on it how you see fit. But the idea is you should have that in your back pocket for this course under the premise that you don't have an internet connection, access to the website, and you may get asked questions related to, you can pick a service offering in any of these areas. If you're in compute, what's the difference between Amazon EC2 and EKS, right? If you were asked that particular question on a midterm exam or a quiz, right? So the same exercise for Google Cloud Platform products. You have the different product offerings listed here. And this is intended to do several things. One, provide you with the awareness of what these companies offer. And then two, understand how they actually are similar within each other. You can see that there's a compute section for Google Cloud Platform, and then you also have a compute section for Amazon Web Services. So you potentially could get asked questions around, what are the compute offerings for Amazon that correlate with Google Cloud Platform? And I'm just thinking on my feet here, but the idea is, once you've collected this information, you should be able to understand that if you have virtual service in the cloud called EC2 in Amazon Web Services, if you wanted to find the corollary in Google Cloud Platform, after you've done the lab, you wouldn't have to come online to actually do it, but you can see here that compute engine is the corollary to EC2 in Google Cloud Platform, right? And so on and so forth.
So sorry for interrupting. But I'm assuming we have to write down the list for every single section of both AWS and Google Cloud, or is it just a specific portion?
It's for all of the sections.
Got it. Thank you.
Okay.
And sorry, my audio was still having trouble. But you answered earlier before class. I missed the AWS only or Google Cloud and AWS.
There's two parts. You should see. Let me make sure that if I flip to student view, right. So this is the view that everyone should see when logged into the course module. For week 1, you have both 1A and 1B. And the difference here, if you hadn't noticed, is that one is focused on Amazon Web Services and the second is focused on Google Cloud Platform. So please do keep that in mind for the first part of this week's labs going into next week. Okay.
Thank you.
Yep. I just assumed that naturally folks understood it, but I'm glad the questions came up to clear the air. Yeah, all right, let's continue on. So as I mentioned, the recording from the first course is here. I've also added a talk by Jeff Dean, one of the distinguished architects at Google at one point in time, who in this video goes at length to talk about the rise of cloud computing. So please feel free to view this or listen to this talk he gave a while back while you're working on the labs or whatnot. If you have free time, I think it's particularly important to hear from industry leaders who have paved the road for cloud computing to kind of speak to the history and the current state of what we understand as the cloud service providers that are available today. Just to recap again in Canvas, we have a syllabus quiz that is due, I believe, on the 15th. So please keep that in mind. We also have the challenges that have their respective due dates. The Python readiness has its challenge here. And then we also have the Lab 1, which is our first lab in Google Cloud Skills Boost. This is a lab intended to provide exposure to 2 different instances of interfacing with the compute services offered in Google Cloud. So at this point, everyone who's registered in this class should have received an email adding you to a listserv for Google Cloud Skills Boost credits. I went ahead and added that not too long ago. So checking here, 64E 2024. So everyone who's registered in this course with their emails here, that's in the administration, should have an email at this point. If you did not get an email, please drop me an email. Also check your spam, just in case it may have landed there. But this should have provisioned credits that are accessible as a pool for us to share collectively for the virtual labs that we'll have for this course. So expect that on a weekly basis as we uncover week to week the newer sections, that a lab will be part of that week's topics. Any questions on the Canvas or this week so far? Will it be from you or deAnza? It will be from, it'll have my name as part of the subject, but let me double check. I sent it to myself as well, just in hindsight of a question like that. But checking my email here. It should say, welcome to Felix Amarua shared group. And it should be an email from Google Cloud. Okay. So if you don't have that email either in your spam or in your inbox, let me know and we'll figure out what happened. All right, let's go ahead and switch on over to our slides.
Just one last question. I'm sorry, I'm full of questions today. I did want to ask, so do we have to provide a extensive description of each of the products that are being provided by both Google Cloud and then AWS, or does it just need to be something like really small?
I don't know what really small means, but it should be enough for someone to read and understand what the service offering is.
I guess really small being I guess a TLDR almost, if that's fine or if that's not fine.
If you gave the deliverable to someone who didn't know anything about it, would they be able to glean enough information to understand what that service offering is? that would be the question I'd probably pose back in terms of how much to add.
All right, perfect. Thank you.
Okay, so and then for future reference, I know some of you are on Zoom here in the audio. We have a Slack chat or a Zoom chat here as well. For purposes of just ensuring that we're being mindful of our peers, please raise your hand in the Zoom chat if you have a question, or you can type it directly in the Zoom chat. I've got another window where I have my eyes on that, so I can definitely address any questions you have, just for the flow of the class, right? All right. So unless there are any other questions on the Canvas or related to this week's labs, just other reminders. I see some newer folks logged into the Zoom today. We have the recording from Monday, or excuse me, the earlier class this week in Canvas, so please do follow up on that if you haven't had a chance. We do have the syllabus quiz, which I just mentioned. They are timed, so be aware of that. In addition to the quizzes, our labs in Google Cloud Skills Boost are also timed. So as a gentle reminder, you'll want to understand how much time each lab will require, or at least will give you before starting it. And in addition to doing that, reviewing the lab, you can actually scroll through the lab to see some of the steps that are going to be required. If a lab takes 1 hour to complete, set aside, an hour 15, an hour 30. And before you start it, scroll through. I recommend scrolling through the lab to understand the scope of what you'll actually be doing before starting it, because of the fact that, as I mentioned earlier, if you do start the lab and find yourself running out of time or having to, answer the doorbell and having to do something that's going to distract you from the timed lab itself, you potentially could find yourself restarting the lab or running out of time, right? So, which will then require another set of credits to restart it. So if you find yourself in that situation for whatever reason, it's fine. Please just let me know that you're redoing a lab because of XYZ reasons. And, that way I'm aware that of what's going on. For the labs themselves, I've also outlined some instructions on how to take the screenshots of each task. Again, that's going to be another component for the labs in which a Word document, could be Google document or whichever you choose, will be the placeholder for each screenshot documenting the steps that you've taken throughout the lab, which will then be uploaded to Canvas for the grading component, right? So keep that in mind. If there are any questions on that, don't hesitate to ask. I know this is the first week, so there's a lot of nuances that folks are still trying to glean, but I'm here to help with anything that might not be as clear as it needs to be. All right. Today we'll talk about the technical definition of the cloud. We'll cover the technology stack, the cloud software stack, and some high-level examples, components in PaaS, IaaS, and SaaS. We'll talk about data center hardware, and then we'll briefly look at computer architecture for GCP and AWS. All right. So bits and bytes. Ultimately, right now, some of you may be familiar with the growth of data that we are dealing with today and where we've come from. I remember from personal experience building computers from scratch, and this was in the late 90s, and you had hard disks that were 1 to 5 gigabytes that cost the same cost of hard disks today, in which you can buy at the terabyte level. So the boom of the internet, the boom of cloud services, the boom behind all of the technology as it exists today have contributed to this growth in data that's now arguably called gold today from a relatively comparative standpoint. But I mean, if you think of yourself as a company, let's say you're Mark Zuckerberg at Meta, what are some of the most important data points that you're measured on, when you're in board meetings reviewing with your investors, right? You're going to be talking about user growth. You're going to be talking about advertising revenue. When you look at what encompasses the user growth at Meta, it's essentially the metadata that's created as a result of the user profiles. And that in itself contributes to data that maps to individuals who can create accounts and businesses, obviously, since they have a small business offering or a business offering. But then also the amount of data that is created as a result of its platform in terms of the content that's created, right? That also is another component of data that plays a role in the consumption of data, the creation of data. And I don't have metrics specifically on how much data a company like Meta is producing from a content perspective, but you can imagine they're likely dealing with the terabytes of data at some level. Another analog you can think of is YouTube. Many of you probably logged into YouTube at some point today or in the past week. And when you think of the size of the content that lives in YouTube since its inception in 2003, the likelihood is probably on the scale here in which we're dealing with either petabytes, exact exabytes, zettabytes, zottabytes, right? The point here is that from the standpoint of cloud service providers, for example, companies that have their own data centers in which they're creating and managing data, this scale is going to continue to grow for the foreseeable future with no real point in which it'll stop, right? So what is the importance of understanding these data points? Well, we'll get into that very shortly, but let's start with some grounding questions, right? So if we're looking at a traditional computer system and its components, the hardware that's made up of, what are some of the different components that folks can think of that encompass a system? Feel free to talk out loud or type into the Zoom chat just to stir some conversation here. Any ideas? CPU, motherboard, GPU, RAM, storage, okay? Anything else? Those are definitely core components. Are we missing anything? We're building a computer today from scratch. You're ordering the parts. Okay, what do we mean by I/O? Input, output, right? Peripherals. Okay, power supply, cables, routers. Okay. All right, I'll let you guys keep listing them there. Absolutely right. Now, this diagram more or less encompasses kind of the groupings of different hardware that encompass a system in which you can have a network layer, for example, dealing with any type of communication between systems. Within the system itself, you have a storage layer. And in addition to the storage layer, then you have a compute layer, which is composed of CPU, GPU, a caching layer, memory, and then in parallel with the system hardware, you have peripheral devices such as monitors that we connect to these systems, external devices, input devices, the I/O devices that were mentioned in the chat, your mice, keyboard, etc. Right? So you can think of this kind of representation in this slide as a single system in its existence at a macro level. Now, if we put two systems together, or n number of systems together, right? Let's assume that they're built identically. Now you essentially have a network that could be established between n number of systems, in which if we wanted to move data from one system to another, the open question then becomes, what's going to be the means in which we can move data from one system to another, right? And some of the variables that can come into play are whether or not the two systems or the n number of systems that we're looking to move data or exchange data from could be what's their relative distance to each other, right? How are they actually connected? What are some of the ways that some systems can be connected? Anyone want to throw out some ideas?
Networking.
Okay. What type of networking could exist?
Wi-Fi.
Distributed network.
Okay. I've heard Wi-Fi, I heard a distributed network. How about a local area network? Does anyone know what a local area network could? What would that entail? Probably connecting the systems with a router and via Ethernet cables, right? Some of you probably have some experience setting that up from the past. Now, in some of the examples that were already mentioned, right? If you're in a local area network or a Wi-Fi, a WAN, for example, connected over the internet, once the network connection has been established, then we can exchange data between systems, right? And the means in which we're able to do so encompass several different factors, factors such as the communication protocol between the systems over the network. And then you also have a variety of different ports to choose from. Some examples of protocol. So before I talk about some that I know of, does anyone know of any examples of protocol or communication protocols that exist over a network?
NetBEUI.
Okay. I see HTTP, yes. FTP, SMTP. These are several different protocols examples in which, depending on, the data that we're looking to exchange might warrant one particular protocol over another. But essentially, these two factors, your ports and protocol selection, can determine the throughput and the the throughput of the data that you're exchanging between systems. And let's say, for example, you're running an FTP from the system on the left, and you have an FTP client. You have an FTP server running on the system on the left, and you have FTP client on the system on the right. Well, what that file transfer protocol allows is for the server side, the system on the left, to be able to broadcast any files on its local hard disk, assuming a path has been chosen, to be available to be queried by the client side, assuming that the FTP connection, the protocol connection established between the server side and the client side, will allow for the exchange of data from the server side to the client side. So you can imagine that you have two systems connected over an FTP network in which you're looking to either exchange or send information from one to the other. An FTP protocol would allow for that exchange to happen, assuming that all of the authorization and authentication is in place to enable that network connection to be established safely and securely. HTTP is another protocol. RDP, there's a variety of different protocols that come into play here. And your choice of ports also comes into play, in which, for example, if you're using a non-secure port, port 80 might be a port number that you might specify in the path, versus 443, which might be a secure port, which might require some type of authentication, some type of certification, in which you can essentially stand up a gate in between a server and a client in this example that would need to have authorization passed in order for the network to be established before any exchange can happen between the two systems, right? So what does this mean for us in the cloud? Because of the fact that, and we're only going to use Amazon and Google Cloud here as an example, because these two service providers provide their offerings via an abstraction as a user interface on the web for us to get access to the virtualized systems that we may be of interest. In this slide, we might provision two systems very identically the same as it's represented here. And in either cloud service provider, we can choose our choice of protocol and ports to essentially either host information in the cloud or query information that exists in the cloud from another source. And in that example, right, the fact that we might be querying information from where we are here in Cupertino, for example, to a system that may be in Taiwan or in another part of the world. I don't know what the actual distance is between Cupertino and Taiwan, but you can imagine that if we wanted to exchange data between systems in those locations, the cloud obviously allows us to do that over a network versus other means that don't make relative sense to do so, right? Any questions on this so far? Okay. So let's come back to the single system for a moment and consider kind of how each of the different areas have evolved. So for if we forget about the network, for example, and just focus on the actual compute layer and the storage layer, today we have components that are controlled using software interfaces. You have desktops, laptops, mobile devices came online after the mobile hardware came available. Apple kind of led and has continued to lead that forefront of the app ecosystem, for example, running on top of the mobile device itself, which is composed of, again, your compute layer, your storage layer. You probably have a mobile device sitting within hand's reach of you. So that system is continuing to evolve, whether it's on iPhone, Android. There may be other operating systems on mobile that folks maybe have access to at this point. But this has kind of evolved. In the days in which we had primarily just desktops from the, I don't know when laptops came online, maybe in the early 90s, but desktops were prominent, from the inception through the 80s. Laptops came online with kind of IBM and Lenovo leading that way, in the early 90s. And then mobile devices came online shortly thereafter, that allowed us to run software on the devices rather than operating system-based utility applications, right? We also have traditional and gesture-based input and output devices that we can interface with. Some of those examples can include IoT devices. You have a Google Home device or an Amazon Alexa. At home here, I have a Google Home device, I believe it is. Let me see if it works. Hey, Google, what's the weather right now? Well, it's here. It didn't work, but anyways, bad example. But in any event, we have these types of devices that interface with us that are either traditional or gesture-based as well. So coming back to the point here is ultimately, we've gone from, building infrastructure to support, your traditional web applications to having services and utilities available that have abstracted the hardware away from us and given us a software interface to allow us to interface directly with those types of hardware components that, has essentially led us to the cloud service offerings that exist to today. So looking at that evolution, you have kind of the mainframe, the PC, the personal computer, and then client-server interactions, which were led by companies like IBM, three-tier web-based applications that led to distributed systems that have then led to cloud offerings such as Google and Amazon. I guess my query set off someone else's Google Home device. So obviously that was a good example that worked elsewhere. That happens to me too, in different parts of the home if we mention Google as a keyword anytime. So, um, oh, okay, I got a couple of you guys there. But okay, so let's talk about kind of the user experience in the cloud. So, um, generally speaking, the experience allows end users like ourselves, whether we're developers, we're a startup, we're at a startup, if we're building, if we're working at a large, Fortune 100 or Fortune 500, we might be at a large company that's transitioning to the cloud, right? Um, in any event, the persona is less important as it is the experience in which the end user is able to execute a use case from a device, typically a laptop or a desktop machine, without any knowledge of server attributes, right? So some of you are watching this on a laptop, some of you are watching on a desktop, but irregardless of our client-side interaction, we can, as long as we have an internet connection, we can access the user interface that's offered by the cloud service providers, in which we can then provision uh, uh, systems that we can stand up for different use cases. So let's start with let's continue on with some questions. So what are some common cloud properties? And I know this might be a question that might have some missing context, but I want to stir the room a little bit to see what folks are thinking as it relates to cloud properties, right? And another way I'd probably frame this question is, if you're building a cloud service provider similar to Amazon or Google for your customer base, right, the different personas we just talked about, what are some of the facets that you'd want to have offered?
Compute, messaging, database.
Okay. Other than, okay, let's say we have our list of all the capabilities that we want to offer in our new cloud service offering to go out and catch up with Google and Amazon. What else should it also have? Let's think of the user experience, right, as one example. I see data transfer between devices if the data is backed up on a data center server. Okay, that could be an existing service offering that Amazon or Google Cloud offers today. All right. Here are some properties. We want it to always be available, right? The analog that I used earlier of clouds operating as a utility, most of the time we don't think about whether or not the water is going to be there if we want to take a shower or if we want to get a drink, right? It's generally there, assuming that we're paying for the utility, right? It's highly available. The same concept should apply for service offerings that if, for example, Dylan, who's offered one service offering, data transfer between devices that backs up data on the data center server, if Dylan's going to go out and pay for that offering, what he's likely going to expect that it's always going to be there and it's going to be highly available, right? He's not going to want, and I'm not picking on you, Dylan, here, but I'm just using your example. He's not going to want to pay for a service offering that transfers data for him, but then, for example, it's down, less than 99.9% of the time, right? Other properties include elasticity, the ability to grow or shrink in size, right? So if your startup now is leveraging Amazon or Google Cloud for its cloud service offerings because of the obvious reasons that make sense for a lean company looking to grow its revenue. Well, your company is growing revenue, right? You're scaling, you're using your user base is growing. If your startup is running in the cloud and doesn't have the ability to grow with your customer base, with your user base, with the metrics that you're looking to accomplish year to year, that potentially could be a problem, right? We talked about the example where seasonality happens, where during Black Friday, holidays, what are companies finding themselves that are operating in e-commerce having to do? They're having to do what? Scale their infrastructure to offset the growth in customers, for example, we're talking about Amazon e-commerce, folks who are going to their websites to buy gifts for the holidays for their families, or and the amount of traffic that typically grows within that seasonality period that warrants cloud service providers to allow for companies, whether it's Amazon or if it's companies on Amazon, to be able to scale their infrastructure to support the traffic that the seasonality periods contribute to. Scalability and on-demand provisioning, another. Being able to take multiple requests at the same time, dealing with concurrency, very similar property as it relates to the seasonality that happens, or when events happen for social media sites in which you get more traffic, spikes in volume, spikes in users coming to a website, or if it's GitHub and spikes in commits and changes that GitHub sees, right? Self-service. Why is self-service important? Well, if you're a cloud service provider, you likely have employees who are helping your customer base, but at the same time, you don't want to have to handhold every single of your customers who are looking to stand up a compute stack using CloudFormation, but have trouble doing so, or coming back to the example of having to figure out how to establish data transfer between devices in a data center on any cloud service provider, right? So in turn, enabling self-service offerings for companies to be able to allow developers, allow their customer base to be able to be empowered and to be able to have documentation, to be able to have very simple instructions in which they can understand how to do so without having to rely on a human being or staff members for support, right? Having on-demand provisioning as well. If you realize, for example, that your startup needs another set of compute instances in a new region to support unknown traffic that you hadn't foreseen, your team should be able to do that relatively quickly for on-demand provisioning, or vice versa, scaling down. Metering traffic, understanding your volume, your thresholds that you set in place. If there's any risk of traffic against any part of your compute stack. Multi-tenancy, what's the distribution of users across the different zones and regions across your compute stack, or your application, right? Yeah. So those bullet points here that we have on this slide really are several common properties that exist that cloud service providers have had to take in consideration, putting the developer, putting the user at the forefront of leveraging their capabilities. Question I see in the chat: would having people to help with issues also count as a common cloud property on a material, like a technician or support team in case something goes wrong, or is this all related to the technical aspect of cloud? No, it's absolutely true, right? Even to this day, you do have access to support staff that work at these companies that offer their cloud service offerings. Generally, the last time, from speaking from experience, the last time I interfaced with support staff was kind of an async chat-based interface in Amazon Web Service for some questions I had. So it's very, I can't say that's representative of all cloud service providers today, but because there are edge cases in which a self-service offering in any cloud service provider may not fulfill a question or a gap or a bug that you encounter, yes, it is required at some level where staff on the ground can help with, issues, questions around a particular scenario. And in fact, some of you might be aware of this already, but as these cloud service providers iterate on the product offerings that they offer, they actually seek feedback from the community, right? You have these B2B relationships that exist between Google and all of its partners, all of its customers who leverage Google Cloud Platform. Same with Amazon Web Services, same with Microsoft Azure, in which they have, a combination of sales staff, product management, and engineers who take in feedback from these customers about either issues with a product offering or with opportunities to improve the product offering with a future capability down the road, right? So that's always going to exist for perpetuity as long as the product offering is available. You will have humans on the ground who likely are based in relatively close by, if not at the locations of the data centers, in which they'll be able to address issues. Let's say, for example, there is a data outage, or a cloud outage in any particular data center, right? Well, as long as that data center has been hit by lightning, someone's gonna, there's got to be support staff there to figure out how to get things back online, right? If high availability and disaster recovery have not addressed the issue, right? So yes, you do have staff support folks who are on the ground. So let's take a look at some of the components that make up the cloud technology stack. Specifically, we talked about just the compute, the single compute system and storage system. Generally speaking, you can think of the different layers in the cloud, starting from the networking layer through storage, hardware, virtualization, operating systems, middleware. You have a runtime layer, and then a data layer, and then applications. And what this stack represents here is just a pictorial view of what's underneath the covers when you go to Amazon Web Services portal and are attempting to provision a compute layer, or not, excuse me, not a compute layer, but a compute instance, or if it's to GCP to provision a compute engine, for example, right? So underneath the cover, what's been abstracted away from you as a user interface in which you can use software to provision that particular service offering is essentially what this technology stack is executing access to you, executing access for you, when in reality, the actual technology stack itself is part of a data center that you're getting a very small portion of access to, right? And we'll double click into this momentarily here. But if we walk down the technology stack here, starting with the application layer, you think, here's where you have the interactions between customer to customer, business to customer, business to business examples. You have mobile and social apps, all running in the cloud. So you can think of these examples. Some of you probably used DoorDash sometime in the past month or so. That's a web mobile software offering that likely uses a technology stack from the cloud. Some of you probably watched Netflix sometime in the past month, or Hulu, or anything along those lines, in which the streaming services that are provided to you are hosted in the cloud somewhere. You also have enablers. We talked about mobile and social network platforms. You have enterprise applications and consumer applications that are fundamentally running on top of the stack or built into parts of the cloud stack. And then you have other trends, that exist as well. At the data layer, some of you might be proficient in dealing with SQL or other types of structured or non-structured persistence. These, you can almost imagine every different type of persistence is available in the cloud. As you go through assignment 1A and 1B for both AWS and GCP, you'll see the breadth of persistence offerings that are available there. Then you also have different kind of service offerings at the data layer, such as Hadoop, if you're interested in taking a large data set and executing instructions on partitioned parts of that data set in parallel, so that you can perform high computation tasks on a large data set. Or you may be interested in Cassandra or Bigtable or MongoDB as other types of databases that you'd like to get access to. At the runtime layer, you have MapReduce, HPC clusters. These are, intended to kind of help with, high computation tasks. Middleware layer, this is typically where you'll have integrations with, examples like API gateway, an API gateway solution such as Apogee, which I believe was acquired by Google, Heroku, Elastic Beanstalk. Examples of operating systems, some of you may be familiar with, what exists today. Obviously, we have Windows, Mac OS, Linux. There's a variety of different, you pick your flavor of operating system that you're interested in. And when it comes to provisioning compute, you can actually choose the OS of your choice, more or less when it comes down to, what you're more comfortable with or what your requirements demand for the system you're interested in. At the virtualization layer, generally, this is where you kind of have abstraction between different layers of, the application and then the underlying runtime environment. Some of you may be familiar with Kubernetes. You might have containers running at this layer. You might have images that you can choose from that are virtualized. So the scope of this layer is essentially another abstraction layer where you have hypervisors, and other types of service offerings such as VMware. By the time we get down to the hardware layer, this is fundamentally where we're dealing with the CPUs, memory selection, SAN and direct attached storage, for example, solid state drive selection. And then from there, we get down to the NAS and SAN, choices around backup and recovery, hot, warm, cold, and frozen storage options, data indexing, what are requirements around, throughput of storage for your requirements. And then network, at the network there, we're typically dealing with, again, choice of protocols, port selection, security. Again, there's two different there's two different perspectives here. One from the user perspective, in which you have your choices that are made available to you from the software standpoint. The other perspective is from the cloud service provider's perspective, where at the data center level, these, the networking layer is obviously composed of the different network devices and network peripherals that then get abstracted to the user in a way in which their choice for configuring any aspect of, setting up firewalls or setting up, any type of gateways, VPNs, are made available as a software offering, a user interface in which you can customly configure that within your cloud computing requirements. So what will happen after going through labs 1A and 1B is you'll understand what, at least from the AWS and GCP standpoint, each of these companies offer within the entire technology stack that you see here. So a plug for our textbook here is, in the CDK textbook, we cover several different topics in the following sections. I've added this section here as a reference, and I don't think I have a link to this in our Canvas module, but this is essentially recommended sections to cover in the CDK textbook that will provide additional context around these areas. What are some of the key terms, again, that may be useful to get familiar with at this point if you're not already familiar with? Differences between memory, volatile memory and non-volatile memory. What is a process, right, on a system, a PID? What is a processor? Different types of storage. The communication protocols across a network, ports, and the different types of ways in which messages can be exchanged. I believe these key terms and a more exhaustive list are added in the challenge that we have in module 010. All right, so we've talked about quite a bit so far. What I'd like to do is take a 7-minute break for folks to at least be able to breathe, take a bio break, get some water. We'll come back at 7:02 p.m. and we'll continue the second half where we'll cover a little bit more about what's inside, and we'll go from there. I'll hang around for any questions in the meantime, but we'll come back at 7:02 p.m. Okay, so we are back, and am I audible? Yes, okay, perfect. All right, let's continue on. So, what is inside the cloud? We've talked about the different layers, as you can see here. Let's take a quick look example at the software stack in the cloud for Amazon as an example, right? So, what do we have here in each of these blue boxes here? Well, each of these blue boxes represents two things. One, a capability, and then two, examples of what may be available for us to get access to as a service offering in Amazon. So for example, here, if we look at a web server, some of you are familiar with how to stand up a web server. You might have the option to provision a web server in PHP, or JavaScript, Java, with your choice of the underlying web server, Tomcats, etc. You might be interested in some form of caching at any part of the entire computing stack. You might be interested in also provisioning persistence of that's composed of several different persistence types, as you can see here: SQL, Cassandra, Dynamo, Bigtable, etc. You also might want to also add, and what's highlighted in pink here kind of represents maybe a sliver of what might represent a proof of concept, or what might represent a simple kind of outcome that you're interested in building, that represents a web application, right? You might want to also add Elasticsearch as part of, querying against the persistence that you have in which you get autocomplete, in addition to other capabilities of services. And then your coordination as you roll out your deployments, right, using Chubby or ZK, right? So the point here is that the idea is, a team, an individual, a small business, a large company can come to the cloud with a use case, an outcome that they're looking for, and a la carte style, choose the capabilities that are offered to create the outcome that they're interested in, right? In this example, we're interested in building a web app that might, perform some series of functions, right? When you look at the macro picture of what's offered by a cloud service provider, you're not going to need everything. And there's never really going to be a use case where you're going to need everything, right? The intent is that, a use case will warrant a subset of what's offered, and the service provider is there to provide um, the utility for those service offerings, so that you don't have to go out and build it from scratch. Now, if we're looking specifically at components that are offered as a platform as a service capability, then yes, you might need to offer more than necessary, right? Because we went from a web application to now a platform as a service offering, in which now your underlying platform running on top of Amazon might warrant different subsets of the underlying services that Amazon provides, but you don't want to offer them yourself. But your platform will then allow developers to build on top of that, that will allow them to leverage, your platform, which is running on top of Amazon, for a variety of different use cases for the developers building on that platform, right? So this is typically the trade-off between using Amazon Web Services for a targeted use case, building a web application, for example, versus companies who are building a platform for their internal developers to build on top of, but are relying on Amazon Web Services or Google Cloud Platform as its underlying infrastructure, as opposed to your company going out and standing up the infrastructure itself, and then offering that platform to your internal developers to build on top of, right? Because of the obvious reasons of the cost implications, CapEx, and operational expenditures that the company in question will have to deal with, in standing up that infrastructure to build a platform in which their developers are building on top of, and then will have to deal with the fact that it's obsolete after several years. So we talked about kind of what's composed of a computing system. Let's hypothetically think of a scenario in which we're walking into a data center. It could be a NVIDIA data center, it could be a Google Cloud data center, it could be an Amazon Web Services data center. What different components would we potentially see in a data center more prominently than others? You want to gamble and throw some ideas out there? Networking, okay, gigabit networking. Let's look at, imagine that, okay, another way to look at this question is for building a data center that's supposed to compete with other data centers, what would we need to go out and buy other than the traditional compute system itself? Okay, we'll need a place for cooling, air conditioning. Data centers need to be temperature controlled. Space, correct. Okay, so I saw some. I saw some allusions there in the chat. Much of what a data center will consist of is, again, when we looked at the example where we looked at two systems in parallel, connected to each other via a network, right, and a protocol port, right. Essentially, a data center is bringing those systems together and stacking them horizontally and vertically in a way in which now you have these systems distributed across each other in a way that allows them to become a much larger system. So network is actually going to be a huge, huge component in a data center, right? You have network interface cards, you have switches, you have routers, you have multi-socket servers, right? You also have GPUs, disk arrays for hard disks, right? Storage. Um, so as a kind of segue before we continue, I'm going to put a link to NVIDIA's recent earnings call back in, I believe it was February, in which Jensen Huang talked about their vision for their next AI data centers. And I highly encourage everyone to take a look at that. So I'll put a link to that in the Canvas module. But anyways, data center hardware, these are just several components here. You're going to have generally rows of rack-mounted servers that encompass CPU, DRAM, disks, GPU, and each one of these different servers that more or less is that compute system gets stacked into a system which we call a rack. And a rack can contain, anywhere from 40 to 80 different servers within a single rack with an Ethernet switch that plays a role within that rack. Now, when you take the servers and build a rack composed of servers, then you can build a cluster composed of racks that are connected to each other via Ethernet switches. And essentially, you would have a cluster switch that also enables clusters to talk to the other clusters. So you kind of have this, what's the word I'm looking for? The fundamental component is the actual server itself, in which you then can build racks, and then in which you can then build clusters composed of racks, right? So this is kind of one way to think of how data centers are composed. I see a question, a server setup is placed in racks, right, where drives are connected via RAID. Yes, so storage is essentially connected as a separate line item. That's why you have the abstraction between compute and storage separate. Storage is also separate for other reasons in which you want to be able to swap out storage separately from compute rather than building them together. in which then you would have issues in which if either the compute layer or the storage layer fails, then you have to bring out the entire system as opposed to having to deal with the abstraction of them not actually being, a part of one system. Now, if a rack were to suddenly shut down, could the entire data center become corrupted? No. So, generally speaking, I don't imagine data centers have not thought of scenarios like this. And typically, let's say, for example, a server fails, right? It will go offline and the rack will continue to operate as is. In a similar vein, if an entire rack fails, just because a single rack within a cluster fails doesn't mean that the cluster is in op, right? It just means that that cluster, or that rack within that cluster essentially would need to be replaced. Each of these racks can stand alone, but it plays a role within the cluster. And if there is a failure in which the entire cluster is threatened, it'll take itself offline from the cluster to prevent taking the entire cluster down. That's the type of way in which you want to architect the composition of servers to racks and racks to clusters, in which you kind of have isolation between each component, where you have fault tolerance in a way that prevents a single point of failure contributing to the entire cluster in this case. So let's take a look at an example of Facebook several years back. It's likely a bit different now. It's likely more relevant compute and server architecture here. But you can see that in this example at the time, Facebook or Meta's strategy in building its systems, again, Meta in this case doesn't rely on a cloud service provider as a whole. They have their own infrastructure, which they've built. But when you think of how Meta operates as a social network, you have a web app or web tier, you have a database tier, you have a Hadoop tier that typically is dealing with all of the the parallelization of the data across different partitions. You have a haystack layer, and then you have a feed layer. But you can see that for each one of these different systems, you have different requirements that have requirements for different compute, different memory requirements, different storage requirement for the use cases in which they're offering, right? So web and chat, has requirements versus requirements for, take for example, storage, right? The storage requirements for the web app are different for a feed, right? And so on and so forth. So you have these different configurations that typically come into play, at least for Meta's example, in which they've customly defined their infrastructure in a way for optimizing against the use cases that they have here. Now, the question then becomes, as a cloud service provider, does this make sense to offer as well? Chances are, yes. Amazon, for example, has its own, Amazon has its own, AWS is separate from Amazon.com, right? So you can think of the relationship between AWS and Amazon.com in a similar way in which Meta has its own infrastructure, and then the actual Meta application, whether it's Meta, whether it's Instagram, whether it's, all of the different components that encompass Meta, in a similar vein for Google, right? Google has its infrastructure, Google Cloud Platform, and then all of the Google applications itself that we use and have been interfacing with run on top of that, while Google Cloud Platform is also made available for companies and developers to leverage as well. Another question or this confirmation: the server itself is self-sufficient, similar to cells, and they end up dying. They separate from the main body, so everything else is okay. Yes. That's a good analog of a way to think about it. Okay, so for folks who haven't already started the AWS exercise, these are the general macro areas that you may run into, in addition to likely newer ones that have been offered since we've collected this. But compute, storage, database, migration, the way these are separated are for reasons in which you might want to come to Amazon Web Services only for using RDS or for S3 or for code storage, right? You have no other use case to come to AWS but for database, right? So it should be simple enough for you to go to the database link and find everything that Amazon Web Services offers for persistence, right? Or for other areas that you can see that are segmented by product areas. We've already gone to the website, so I won't go to it again. I believe this, let's go to this link here. Okay, so this is a slide deck that talks about a little bit more about the high-level components of AWS. So I'll share this slide for us to have access to as a group. So for example, if we clicked into compute, you can see the different layers within compute that were offered at the time. This has likely been extended to include additional compute products that are offered by Amazon Web Services today. Some of the naming may have changed. In a similar way, you have Google Cloud Platform as well, in which you have similar groupings, but different product names, different similar product offerings, right? In which if you're a developer and you're trying to figure out, okay, well, I know I need compute, I know I need storage. My startup is going to leverage these from the cloud. Do I choose Amazon's compute? Or do I choose Google Cloud's compute? Do I choose Amazon's web server, storage? Do I choose Google Cloud storage? So many companies have to make these trade-offs, whether it's cost related, whether it's some of the finer details in terms of what each service provider offers. One of Google Cloud's strong suits is the fact that it offers TensorFlow and TPUs as part of its cloud platform. So many companies have leveraged Google Cloud Platform for that reason, whereas more recently, Microsoft Azure partnering with OpenAI has obviously a foothold on kind of what's happening in the AI space. So companies likely have leaned towards Microsoft Azure versus leveraging AWS or GCP for native AI use cases in which they have access to GPU infrastructure. Not to say that that's not offered in AWS or GCP, but generally the choice is going to be up to the company or the individual based off of their requirements in which they're interested in. So looking into the compute layer, for example, the question might now become, well, which of these compute offerings makes sense for me? If it's compute engine, this is the infrastructure as a service offering, all the way over to the managed services, which are automated elastic resources that are catered towards more of a dynamic type of infrastructure versus a self-managed infrastructure offering. And then obviously you have the flavors in between for different use cases. I've already answered the question about the list of the offerings, so I'm not going to belabor that point again. Why would you want to become a cloud provider? Other than the extrinsic reasons behind becoming as rich as Andrew Jassy or Jeff Bezos or Sundar Pichai, why would you want to become a cloud provider? You're going to start one today. Any ideas? No ideas? It could be fruitful. Well, other than making a lot of money, right? Maybe you see a gap in what current cloud providers are offering, right? Maybe it makes sense for a company to leverage existing investment at low incremental costs, right? You want to create a new revenue stream, right? And the idea is that there's likely entry point, that might not impact the cost to get it stood up. Do you want to defend a specific franchise or a specific company, right? Azure, for example, could be offered to companies already using a suite of Microsoft applications. Maybe you want to attack Google. Maybe you want to attack Amazon. I don't know. Perhaps it's leveraging customer relationships, or if it's becoming your own platform, right? Facebook decided to build its own infrastructure, and then as a result, has been doing so for, since they've been doing that, right? I don't know specifically the date of that, but the idea is these are some reasons why it could be advantageous to become a cloud provider, but that ship has been sailing for quite a while, right? So if the question became today, does it make sense to become a cloud provider? Well, the argument might be, well, what type of cloud provider do you want to be, right? And this comes back to the point of understanding where the industry is today and where it's going. And most of us are probably familiar with the fact that AI has kind of revolutionized, the way applications have been built and will be built, and how they play a role in the industry at large, right? So if we looked around and asked ourselves how many AI data centers are around, well, it's a good question to ask, right? Because there's a likelihood that will start to become more prominent in the future, in the wake of what NVIDIA wants to do, in the wake of what AMD likely wants to do, et cetera, right? So some questions for fostering more thought around cloud computing as a whole. I'm not going to read through all of these, but what are some of the paradigm shifts that we've seen in the past that make cloud computing slightly different, right? And by paradigm shifts, what we mean is, coming back to the evolutionary slide where we went from mainframes to the personal computer, when mobile devices came online, or, from a, industry standpoint, when the sharing economy became prominent. Prior to Uber and Lyft, many of us would hail a taxi to get from point A to point B, right? But that paradigm shift essentially changed how both consumers and businesses, decided to, travel from point A to point B, right? Which also influenced the food industry, right? You can order food from where you're sitting right now and have it delivered to where you're sitting right now in probably less than 1 hour, right? Which didn't exist, 12, 15 years ago, right? So these are additional questions that I'm hoping that can foster some more thought and questions for the purposes of this course. Again, I've already talked about what this week will entail, which is what we have here. I'm also going to make available a reading assignment, which I have not made available yet, but it is titled, I believe it's it's titled Above the Clouds, a Berkeley View of Computing. So that will be brought into scope. Actually, let's do it right now. We're going to bring that in to the current week. So that link is available now for consumption. I will have office hours on Saturday and Sunday from 1 to 2 p.m. if any questions do come up between now and next week. Do we have to do a spreadsheet for it, or should we do it as a document instead? It's up to you. Spreadsheet might be more structured and organized for you. But if you decide to use a Word document, you're not going to get penalized differently. I mean, you won't get penalized because you've chosen a Word document versus a spreadsheet. Outside of that, that's all for today. I'll hang around for any questions, but thank you all for today, and we'll continue on next week, in which we'll go into the technical definition of the cloud, and then also everything as a service business models and their benefits, along with factors in managing the cloud. So stay tuned for that. Thank you.
Thank you.
Thank you.
Thank you.